Yeah, not
So
a
she
big
said,
deal. Yeah, we've
wait,
got,
so
what's that?
what is that, Zurich? Yeah, it's not clear. She said she was gonna on what day was that? Maybe 2 days ago. She said she had 2 more days in Greece, then a day or two in Zurich, and then back to New York. So I'm gonna guess that she's not joining. If she does, like you said, we'll backtrack. So
Right on. Yeah, right on. Yeah, so I'm super excited because this is weather happens to be of super interest to me. Just the sheer I guess depth at which you have to understand the atmosphere to really understand how weather works is kind of fascinating to me. So consequently, this session has a ton of material. I am forecasting that I'm going to run out of time on some of the slides. So, but the good news is we've got 2 sessions scheduled for weather. So we can kind of whatever I don't finish here tonight, we can pick up with next time, which is not a big deal. But anyway, let me share screen here, and we'll start rocking and rolling. Okay, is that showing up for you?
Yes, sir.
Okay, so there's 2 sessions scheduled for weather discussion. This session is more weather theory. We're going to talk about the foundational science behind what causes the weather patterns on Earth. And then anything we don't finish tonight, we'll pick up with during the next session. In addition, we will next session transition into topics concerning weather tools, like in-flight weather tools, pre-flight planning weather tools, weather services that are offered by air traffic control, services that are offered by the National Weather Service and whatnot. So we're talking theory tonight, and then next session we'll transition into like weather services and practical application.
Okay.
So at the very highest level, the most foundational aspect of weather on the planet Earth, the weather that we see every single day is caused by one single item, and that is the sun. The sun is solely responsible for the weather patterns on Earth. And to go a little bit deeper, the sun causes heating on different areas on planet Earth, and that differential heating across Earth is what causes the weather to occur. To take it a step further, if you remember that chemistry equation, PV equals rho RT, the ideal gas equation that we talked about when we were talking aerodynamics. As you adjust temperature in an ideal gas, pressure changes. So when the sun heats the Earth, you've got all sorts of things happening. Temperatures changing, which is causing pressures to change, and it's causing air to move. And as air moves over different terrains and bodies of water, it picks up different moisture levels. So that's kind of the start of the whole cycle is the sun. It causes the heating, the differential heating on the face of the Earth, which starts a whole chain reaction, which we call weather. Once we kind of understand where the whole chain starts as far as differential heating goes, we can have a discussion on air circulation and pressure differential. Obviously the sun can only really heat one area of the Earth at a time, or one side of the Earth. Like in the summertime, it seems like the hottest point of the day is in like the mid to late afternoon here in Texas. And it's obviously not as hot when you wake up in the morning, and it's still hot, but it's like not as hot when you're going to bed. So those differential heating causes pressure differentials, which in turn causes the air masses around Earth to actually cycle, to move. And that picture there in the top left is kind of just a crude, high level graphic that shows as the sun heats the Earth, the different flow patterns of the air mass as they go around the Earth. It truly is air masses flow kind of towards the equator, and then they turn around and flow back towards the poles, and they turn around and flow towards the equator. And we can attribute this to the heating and the cooling of the air masses. Of course, hot air rises, and when you've got a vacuum or a void that's created by that risen air is replaced by cooler air. That air heats up and rises, and then it gets replaced by cooler air, and the cycle continues. So the sun causes the heating. The heating temperature differential causes the pressure differential in the rising air. And of course, as air moves, it's replaced by air, and then it heats up and starts a cycle all over again. And then to add kind of a different element or an additional element, the Earth's rotating. So you've got this this circulation of air mass occurring on Earth's surface and in its atmosphere. And that circulation, at least in the textbooks, or if you read the pilot's handbook, it calls it the static circulation. But as soon as you throw in Earth's rotation, which isn't slow, Earth rotates, I think, at a speed of about 900 miles an hour. At our latitude, like in Texas, the surface of the Earth is rotating at about 900 miles an hour. The flows become distorted, and they distort to a certain direction depending on whether you're in the northern or the southern hemisphere. And so, if you can imagine, if you've got like this sphere, call it Earth, and you've got these flow patterns in the sphere, right? And then you spin it like a basketball on your finger, those flow patterns are going to distort, right? Just based on the momentum of the spinning sphere. And that distortion is called Coriolis. It's called Coriolis force. And the reason this is important, the reason this is a foundational element to understanding weather, is it is, I'll call it just one of the curveballs, the Mother Nature curveballs that is thrown in, which is why weather is sometimes not very predictable. If the Earth and the air mass flows were static like they are in the top left picture there, weather would be much more predictable, because the sun is always over a certain part of the Earth at a certain part of the day during a certain part of the year. And so the fact that the Earth spins and causes this Coriolis force is one of the major reasons why weather is significantly unpredictable throughout the year. Any questions on that material before we move on?
No.
Okay. So, one of the major elements to understanding weather is one of the simplest things that we all learned kind of in science class when we were kids. The fact that hot air rises. That principle, it shows up time and time again when you are studying weather patterns, when you are looking at your weather map during a pre-flight planning, trying to determine what kind of weather you're going to encounter over your course or during your trip. And the thing that always comes back, fundamentally speaking, that you always run into is the rising of air due to temperature and pressure differentials. Once we understand, how the sun affects weather on Earth through the heating and then the static and distorted flows based on the heating and the Coriolis force, the next fundamental element that we need to become familiar with are pressure systems. And pressure systems are a direct effect of the aforementioned heating and movement of air masses. This particular model that I have here on the screen is I'll call it extremely simplified, just to make sure that we understand exactly what pressure differentials and pressure systems do. But at the very simplest way I can explain it is, as air rises, as air heats up and rises, a void is left in the area that air mass once was in. And because Earth's atmosphere is not losing or gaining any volume of air, simple science would say that as soon as that air rises and leaves that void, air has to come in to replace it. You know, there'd be a void, there'd be a vacuum, right? Something has to come replace that that missing air pocket, and and that's what causes the high pressure, low pressure interactions on Earth. Air rises due to heating and leaves a void, a vacuum, an area of low pressure. And as we know, air moves from areas of high pressure to low pressure. Oh, hello. Air pockets move from areas of high pressure to low pressure. And so you get high pressure air replacing that vacuum, that area of low pressure. And the cycle continues over and over again. So again, as air heats up, as the sun heats the air in the atmosphere, it rises, creating a void or a vacuum where that air was, and that would be an area of low pressure. And because air moves from high to low pressure, you have these areas of differential pressure, low pressure areas and high pressure areas. Hot air rises, cold air sinks. Make sense?
Yes. Question on the directions. Do they change from northern hemisphere to southern hemisphere based upon the Coriolis effect?
I don't believe so. I think the high pressure and low pressure centers always flow in the same direction, counterclockwise, clockwise. I think I'm pretty sure about that. Let me look that up.
Okay.
I know your toilet flushes the other direction in the southern hemisphere.
I've been told that. I've never validated it.
All right, I took a note on that. The important principles to kind of remember moving forward is you can never have a vacuum in space inside Earth's atmosphere. There always has to be air occupying space. And so in order to do that, because of the air movements, you've got air moving all the time from areas of high pressure to low pressure. Over and over again, the cycle continues. Oh, hey, I even have it on my own slide. You're 100% correct. Look at that.
There we go.
Hey, there you go. Man, look at you. So yeah, the other item that's important to know, especially when we start talking about thunderstorms, which occur in areas of low pressure, is that your high pressure areas are air moving down towards Earth and in a diverging pattern, and then if clockwise in this hemisphere, counterclockwise as you mentioned in the other hemisphere, and then the low pressure areas are what they call cyclonic, and they converge. They move up and they converge. and the cycle continues over and over again. From a big picture perspective, I put this picture over here in the top left of a high pressure and a low pressure system next to each other because it's kind of an ideal state. But truthfully, in the low pressure area, the air is moving up and it is converging, and it spits itself up literally at the top of Earth's atmosphere. It spits out and gets sucked in to its buddy over here, the high pressure center, and it shoots down towards Earth's surface and diverges. So this is kind of an ideal state because you've got two pressure centers next to each other, but that's literally what happens. And you can probably bet that in this area right here of where the pressure centers are next to each other, it's going to be pretty windy, I would guess, because you've got a lot of air movement happening. So again, the low pressure shoots up and it converges, and the high pressure shoots down, diverges. Okay, do you remember what the standard temperature is at sea level?
15 degrees Celsius.
Yep. Do you remember the Fahrenheit, just for kicks?
59.
Yeah, man, you have been studying this stuff.
Yeah, so there's still some areas that I struggle with.
Yeah, that's right on. And then this was a question that I think you got correct on the Slack a couple weeks ago. The weather people, they use a term called lapse rate to describe the change in the atmospheric conditions as you move up in the atmosphere. And there are several different standards. You can search online, and I'm sure there's a list with all of them. But the absolute standard lapse rate for a standard atmosphere is a decrease in temperature of 2 degrees per 1,000 feet. That is, if somebody asks you what the standard lapse rate is in a standard atmosphere, you would say 2 degrees decrease centigrade per 1,000 feet.
It's also, I think, 1 inch mercury per 1,000
Yep.
feet too, right?
You got that right. You bet. And that actually, I saw you answered the question. I haven't had a chance to look at it, but that particular fact comes into play in that question I asked on Slack.
Yeah, I'm not convinced I got it right, so it may be worth discussing at some point.
Okay. Definitely. We can look at it right after. And then there's a couple other lapse rates that are good to know. There's one called the dry rate, and that's 3 degrees centigrade per 1,000 feet. And then the wet rate, or the moist adiabatic rate, 1.1 degrees Celsius per 1,000 feet. There's also another one. I don't know if I put it on the chart here. Yeah, I didn't. That's called the convective rate. And it is, going off memory here, it's 4.4 degrees Fahrenheit per 1,000 feet. And that is the lapse rate that you use in a unstable atmosphere, in what's called a convective atmosphere. But the one you're going to want to know is the 2 degrees per 1,000 feet. And you're also going to want to know the convective one, because that one comes up on the written test. And we are going to talk about atmospheric stability here on the next slides. But important thing to know, just as a precursor, is the faster the temperature drops as you go up, the less stable your atmosphere is. Now let's keep, in effort to keep some of these concepts tied together, the pressure centers, your low and high pressure centers. Your low pressure center, if we go back a couple slides, that's your pressure center that has vertical motion upwards, okay? And so as your air is moving upwards at a significant rate, let's call it, your temperature is going to drop. The air mass is going to cool significantly as it goes up. The faster it cools per given altitude, the less stable your atmosphere is going to be. And you can also kind of equate this loosely to the velocity. If your air is moving in a low pressure center quickly with high velocity upwards, it's going to cool very quickly, and it's going to be less stable. Think about like a thunderstorm. The vertical movement of air moving up a thunderstorm in a low pressure center is significant, and the amount of temperature drop is significant. So just as a standard concept, know that the faster your temperature drops with altitude, the less stable your atmosphere is. The bumpier your ride's going to be. And then there's another important concept to remember, and that's what's known as a temperature inversion. In a standard atmosphere, when you're talking about standard day, 59 degrees Fahrenheit, the 1 inch of mercury per 1,000 feet, and when you're maybe you're solving an equation on a written test, or maybe you're doing a performance calculation from your pilot's handbook. Your standard lapse rate is obviously going to go from warm at the surface to cooler and cooler and cooler as you go up. Like this picture is showing right here. Okay. Another concept that we want to become familiar with is what's called a temperature inversion. It is when you have actually surface temperature rises as you go up, and instead you have an area of warmer temperature above an area of cooler temperature. And the most common, and the reason I put these icons here is the most common type of temperature inversion is after the sun goes down. Immediately after the sun goes down, the surface of the earth cools off faster than the atmosphere. And so you've got cooler air near the surface and warmer air, somewhere in the neighborhood of 4,000 to 10,000 feet above the surface. Now, during most, 80% of your flying, you're going to have a standard atmosphere where the air cools as you go up. But if you're doing your flight planning and you're looking at the temperatures aloft and you notice that it goes up as you go up, then you've encountered what's called a temperature inversion. Temperature inversions are typically pretty stable. And the reason for that, I'm trying to tie some concepts together. The reason for that is because air doesn't really have anywhere to rise. You've got this warm air here, right? And this air here, because it's cooler, it's not going to rise, right? It's going to stay put. It's going to stay in this little box. And so long as you don't have air rising, you're not going to have any convective movement. You're not going to have any temperature decrease. And remember, as temperature drops, so does your stability. All makes sense so far?
Mm-hmm. Yes.
Okay. So we talked a little bit about stability and how that relates to temperature. So stability of the atmosphere, by definition, is the resistance of the atmosphere to allow vertical motion of an air parcel. Even in an ideal state, when you've got a beautiful day out and you can't even feel a bump of turbulence, there still is rising air, because the sun is, if the sun's out, the sun is heating the air and it's rising. But the velocity, the rate, or the aggressiveness for which the air rises determines how stable the air is. And here's this term again that I used kind of earlier, convective. So if you, like I said before, if you've got a higher than standard lapse rate, meaning you've got a higher temperature decrease with altitude than is standard, 2 degrees, you're going to have what's called a convective lapse rate, or I've called it a convective current here. You'll use this term. When you're doing your pre-flight planning. If you talk to a flight briefer, if you call Flight Service Station (FSS), and they use the term convective, They will use that interchangeably to kind of mean that the atmosphere is not stable. And if there's sufficient moisture in the air and the right ingredients, you'll have thunderstorms. So, and then here's this equation again. I want to touch on this because if we can geek out for a minute, I want to make sure some concepts are covered. Here's your ideal gas equation, PV equals rho RT. And for review, this is pressure, volume equals density, constant, temperature. Okay, and the constant's always constant so long as the air has the same types of chemicals in it, and it does. So there's one major concept, and this kind of again ties in some things we've talked about, but in order to kind of further define how quote unquote dangerous a convective current might be, we want to know whether we're going to like run into thunderstorms or what kind of weather we're going to run into. We need to start introducing the concept of water vapor and moisture, because of course, moisture being one of the main ingredients for precipitation, we're going to start putting the puzzle pieces together to define weather systems and what causes rain, what causes thunderstorms, what causes clouds, and the like. So this will be kind of our foundational concept. One assumption we have to make that I'm not going to prove or anything, but water vapor is lighter than air, and this can be I'll say observed just by looking at clouds. Clouds is visual water vapor, and clouds tend to not sink, right? They float. So you could say that's a good way to observe that water vapor is lighter than air. And because of this, a low moisture air mass characterized by higher density. So dense air sinks weight, and the atmosphere is stable. So if we've got a higher density air pocket, that air pocket relative to the air around it is going to tend to stay where it is, or maybe it'll sink. And remember what we talked about, when air is not rising, it's considered to be stable. The converse of that, the opposite, a higher moisture air mass is characterized by lower density. So lower density air pockets are going to rise. And if you remember, air pockets, air mass that rises compared to the air around it is going to be less stable. And then, of course, the speed or how aggressive that air pocket rises will characterize just how unstable it really is. So things to remember, just as a review. As your lapse rate gets higher, you've got more unstable air, to the point where you might reach what's called, your convective lapse rate, which is 4.4 degrees Fahrenheit per 1,000 feet. And then moisture, which is going to be the crux of the weather patterns discussion. If you've got an air mass of high density, that's characterized by low moisture, and that because it's so dense, it's not going to rise, and you're going to have a stable atmosphere. And then just the opposite, lower density has the potential to have higher moisture, and so that air is going to rise up through the atmosphere, less stable. Does that all make sense? Does the connection between density and moisture make sense? I kind of just have it on the screen. I can explain it if you want.
No, it does. It also, in my mind, it has to do with how close the water particles end up coming together. The closer they are, they do tend to stick to each other. And we'll get a little bit more about that with dew point. But yeah, I get it.
Yeah, that's a good way to put it. Exactly. So if an air mass has high density, all the air molecules are tightly packed, right? So there's less room for moisture to be present.
Right.
Yep, perfect. Good. All right. Now kind of just continuing to connect some of the theory, so we started with the sun heating the earth, causing the flow. Coriolis screws up the flow. Pressure centers are created because of the temperature differentials and all that. And then we just talked a little bit about stability and how stability is impacted by, the rate at which air moves in a vertical fashion due to the pressure centers. So to kind of continue on the thread of stability and close out the stability topic, which I kind of hinted at in the prior slide, the ingredients of moisture and temperature determine the stability, and the stability of the atmosphere truly is, if you want to say the sun causes the weather, well, then the sun causes the stability, which causes the weather. And it truly is, that is a true statement, because when you're doing your flight planning and you're talking about different weather patterns that you're going to fly through, the kind of the crux of the discussion is, okay, well, how stable is the atmosphere that I'm flying through? Is it extremely stable, meaning, just going to be great flying weather, or is it extremely unstable, which means I've got like 6 different things I got to worry about: thunderstorms, turbulence, icing, you name it, right? And so kind of as a kind of just to keep harping on the point, if you've got low moisture, cool conditions, and you've got a very stable atmosphere. There's not much vertical movement. The air at the surface doesn't want to rise quickly. And on the opposite, if you've got moist air, in other words, high humidity and relatively warm, you've got a relatively unstable atmosphere, wherein the atmosphere is promoting vertical development, convective air movement, and so you're going to see some of those weather phenomena that we're going to discuss later: thunderstorms, hurricanes, tropical cyclones, those kind of things, icing, that kind of stuff. And you can even see it today. Like I don't know what the weather was like for you guys today, but on a typical summer day in Texas, you can have just the nicest morning, sun's out, no clouds, and by the afternoon you've got these like towering cumulus clouds, these big puffy cumulus clouds that look like they're tens of thousands of feet high. That is an indication of an unstable atmosphere, and we're going to get into that in a minute here. Okay, and you understand this, so I think I'm going to skip over this or talk it briefly. But you understand the fact that warmer air is less dense and can hold more stuff, such as moisture. We just talked about that, right?
Yes.
So this is just kind of dives into that a little bit deeper. But there is a couple points here we'll touch on as far as moisture goes. And honestly, I didn't know this until I started flying. And this is kind of a cool factoid, but do you know how much, just is it kind of more trivia than anything, but do you know how much, what percentage of volume in the air moisture can hold? Like if you've got a pocket of air, what percentage of that pocket can be moisture at any given time?
Actually, I don't know.
This is kind of cool, because usually when you're watching the weather and you see like, oh, 100% humidity, it's real thick out, it's like some people make the comment like, oh my gosh, it's like so thick out. Well, you can only have 4% of any volume of air occupied by moisture at any time. So when somebody says 100% humidity, what they mean is 4%.
It's 100% of the theoretical maximum.
That's right. And if they say 50%, then it's 2%.
Got it. No, I had no idea. That's really interesting.
Yeah, pretty neat. And I say that, I don't know if it's linear, but that's kind of how, after I heard the 4% thing, that's what I tell people. But anyway, yeah. So whenever you're talking humidity, you're really talking relative humidity, and you might have heard that term thrown around, relative humidity, because it's from a relative perspective, how much moisture can the air hold. And then along the lines of talking about moisture, the other term we want to get really familiar with is dew point. And dew point is the temperature at which the atmosphere can no longer support water vapor. So that's the temperature at which the air has reached the 4% point, and now any other water that's added to the atmosphere is not going to be in a vapor state. It's not going to be in the air. It's going to be rain, or frost, or snow. So when you walk out of the house on a Saturday morning and it's kind of foggy out, got a lot of dew on the front yard, well, that you can bet that the temperature and the dew point in the air that you're standing in is probably about the same. So from a pure definition standpoint, dew point is the temperature at which water condenses in a given atmosphere. Does that make sense?
It does.
Cool. All right, awesome. Now, okay, there's all these, weather is so fascinating. There's all these concepts to try to connect. So we've talked pressure centers and air movements, and low pressure vacuum replaced by high pressure, and the cycle continues. And then throw in the moisture element and the fact that not only do we have air pockets moving about the atmosphere and losing temperature and moving to areas of higher pressure, but we also what this creates is what we call weather fronts, weather systems. As you look across the United States weather map, you've got all this air movement taking place, temperature changes, pressure changes, and different areas of the country have, different air masses have different moisture content. And so the ingredients of all of that create specific weather patterns for a given day, or a given point in time. And the National Weather Service uses what's called a term called a frontal system to describe these different weather patterns that move across the United States. Now, I'll tell you what. One of the things that always stumped me, and maybe you've been studying weather for a while, maybe you know it better than I do, but one thing that always kind of got me is the difference between a frontal system and the kind of weather that it produces. Because where I grew up, if you had a frontal system move through, you got rain, typically. But that's not always true, depending on where you are in the country, because you might have different moisture content, right? You might live near, say, the Gulf of Mexico, like you do, and have a totally different weather picture than living in like Las Vegas or something like that. So it's interesting to understand the theory behind frontal activity, so that you can kind of predict what kind of weather you're going to see as you do your flying. So, from a definition perspective, it's important just to know that a front is, you can think of it as a boundary layer between two air masses, and these air masses have different characteristics. Certainly, you've heard the terms, cold front, warm front, stuff like that. So we're gonna dive into fronts. And just so you know, I think you told me that you picked up a commercial study program for the written, right?
Yes.
Okay. Yeah. Have you looked at, if you look at the weather stuff, you'll kind of notice as far as the theory goes, you're going to want to know what kind of weather you can expect in these different frontal areas. And what's nice is there's not an indefinite amount of options here. There's only a few. But I'm going to try to explain the theory behind it, and then really for the test, it'll be good if you understand the flying weather, the application aspect of it. But let's talk warm front. We're going to talk warm front, cold front, occluded front, in that order, I believe. So warm front is simply a warm air mass taking over a cold air mass. You know, you're sitting in cold conditions, warm front moves through, and, you know, for us, we feel as though, hey, it just got warmer out, right? And there might be some rain that goes along with it. But typically with warm fronts, you have high moisture content that moves along with the front. And, you know, trying to connect a couple theories here. This kind of makes sense, right? Because the warmer the air is, the less dense it is. If you remember the PV equals rho RT equation, you know, assuming an ideal state, as your as your temperature goes up, your density goes down. And so you've got more room for moisture. So typically, not always, but typically speaking, warm fronts have high moisture content. And then as your warm front advances on the cold front, using some concepts that we just learned, of course, the warm air is going to rise. Right? The warm air is going to go up. It's going to favor the upward movement. The cold air is going to, if anything, push across the terrain. And so as that moisture starts to move up with the front and rise, what does temperature do?
Decreases.
Yep, temperature decreases, exactly. As temperature decreases, it reaches the dew point for that specific atmosphere. And as it reaches the dew point, it condenses, and then we have clouds. If there's enough moisture in the air and it condenses, and it's too much moisture for the atmosphere to hold, it'll rain. That's how we get warm front rain showers. That exact phenomenon right there. So when you're doing your flight planning and you're looking at your course and it looks like you're going to fly through a warm front, if there's enough moisture content in the air, you're going to run into precipitation. If it's cold enough, it'll be snow or sleet. And the visibility is going to generally be poor because you've got that condensed air in the form of clouds. If it's not obvious, as you fly through the front, your temperature is going to increase. So that's kind of one way to determine where you are relative to the front, is kind of look at your temperature gauge in the cockpit. So that's the warm front. Does the theory behind that make pretty good sense?
It does.
Cool. Now the cold front. Cold fronts are excellent, especially this time of year. Do you guys? I probably should have studied Houston weather a little bit more before this session. Do the cold fronts come all the way down to you guys or not during the summertime? Awesome.
They do on occasion.
Yeah, it's funny when you've got a cold front coming through, you're like, oh my God, thank God, and then the temperature only drops like 5 degrees.
Exactly. You can notice that though. That makes a difference.
Oh yeah, no, it totally. So the theory behind the cold front, of course, it's the opposite. So you've got cold front encroaching on warmer air. And the theories that we connected prior, as far as warm air rising, they hold true in this scenario too. So as the cold air comes in, it literally wants to replace the warm air, because the warm air wants to rise. The warm air wants to rise because it's warm. And the difference between this and the warm front is, the encroaching warm air, it wanted to rise, so it kind of ramped up. But in this case, your cold air is kind of plowing its way through. It's like a snow plow. And it plows its way through and pushes the warm existing air upward. Now, cold fronts are more dense, which kind of explains that phenomenon. It wants to plow its way through and sink and stay low. But what it also does in the warm air parcel is it pushes that air up, and if that air has sufficient moisture, you'll have the same phenomenon that you do on the warm front. The air is going to rise, the temperature is going to drop, the temperature is going to hit the dew point, which is going to cause the air the moisture to condense. It's going to create clouds, and you're going to have that whole phenomenon over again. The only difference with a cold front is because the air that it's replacing is warmer, that air has the tendency to hold significantly more moisture than in the prior example, where the cold air was being replaced. If the ingredients are right, and we're talking Texas in July, or hell, Texas anytime between like April and September, and the air has sufficient moisture in it and it's hot enough and it rises quick enough in a convective atmosphere, you have major thunderstorms. So the main difference between warm front and cold front is a cold front is conducive for convective type activity. Now you still have the potential for convective activity with a warm front if the ingredients are right, moisture content, stability, etc. But cold front, it's much more common because the air being replaced is already hot, already high moisture. And if the stability is just right, or the instability for that matter, you have quite a really nasty weather patterns. Now, warm front and cold front are by far your most typical weather patterns. As you do your flying, you're going to be flying through one of those two fronts. The third type of front that you're going to have to know is what's called an occluded front. And these are these are really strange and difficult to understand at first, but it is the result of a warm front, cold front frontal boundary colliding, where you've got the mixing of two weather systems that you can't exactly characterize as warm overtaking cold in the case of a warm front, or cold overtaking warm in the case of a cold front. This is, cold front approaching warm front, but warm front rotating around and catching back up with the cold front and mixing on its backside type. This one you kind of have to think in 3 dimensions almost. And there's 2 classic cases of an occluded front. You've got a cold front occlusion, where you've got cold air encroaching on cool air. So it's not warm air, but it's cool, because it's already kind of been warmed up by a warm front, right? So let me get the marker out here. So imagine we've got a warm front right here. Well, this warm front has already kind of warmed up this air right here. So it's not cold in relative terms, it's cool. Well, the warm front did not move fast enough. It's now being encroached on by a cold front. So the cold front is cooling the warm air. It's also further cooling the cool air. And this type of weather pattern has the potential to get really nasty, because you've got more air movement occurring. You've got temperatures changing all over the place. And you've got, depending on how fast the fronts are moving, you could end up with a total cold front. This cold air could take over everything, and you could get that convective type activity. So just know that a cold front occlusion occurs when a cold front attempts to take over a warm front, and that warm front has already attempted to take over a mass of cooler air. Does that make sense?
It does.
Yeah, it's like so much stuff going on. You also have what's called a warm front occlusion. And this is when a warm front is attempting to take over a cold front, but unlike this example, it's not as successful at cooling the air, right? This air stays cold, and you've got a cold front encroaching on the warm air, and because of the temperature differential, because this air is warmer than this air, this cold front attempts to cool this air quicker than it does this air right here. And this graphic's trying to show that, right? It's trying to say, hey, I'm trying, I'm focusing all my energy transfer on this warm front right here as opposed to this cold front right here.
Energy transfers like differentials.
Right, exactly. Yeah. Now because just in time for class, there was a occlusion occurring. Let me see if I can find it. France. And they're not really showing it on the map anymore. It was there earlier today. Oh, it kind of is. Let's see. Sorry, I got to zoom this up a lot to show it. But okay, so here's the blue line here in the middle of the screen is a cold front, okay? And the red line here, the red semicircles, is a warm front. And without studying it too much, you can probably assume that they're moving left to right. And then this purple line here, which is just a little itty bitty purple line, that's an occluded front. So that is, as we just explained, we've got the cold front here attempting to overtake the warm front, which is ahead of it, and then causing this occluded front right here, where it's already doing that mixing. Now, there's no symbols on that purple line, so I can't tell whether it's a cold or a warm occlusion. But that's what's happening there. And then, like I said, you can geek out on this stuff, and it's important to, but the weather patterns that exist around these occlusions tend to be somewhat nasty, depending on the things we've already talked about: moisture and stability. You can have any of these fronts, warm, cold, occluded. You can have any front move through, and if you don't have sufficient moisture and the air is stable, all you'll notice is a temperature change. You won't have any precip, any nasty weather. So it's definitely not the rule that there's nasty weather with fronts. It's dependent on those factors. And then, so we talked about the symbols there ahead of time. So warm front, cold front, occluded front. And then you've got the last front, which doesn't really have its own slide talking weather, is stationary front. And that's when you've got a cold front and a warm front right next to each other, or, a cold air mass and a warm air mass right next to each other. But the atmospheric conditions, the air movements caused by the pressure differentials, aren't great enough to cause one to overtake the other. The cold's not overtaking the warm's not overtaking the cold. They're kind of just hanging out next to each other. And I believe I think, did I see that on the chart? Yeah, we've got that over here, kind of over in Arizona, New Mexico. And oh, by the way, from a symbol standpoint, we're going to touch on this next session too, but the direction of the symbols, you can identify where that air mass is. It's always behind the symbol. You can think of it two ways. The air mass is behind the symbol, the way it points, or it's moving in the direction of the symbol. So in this case, the warm air mass is here to the south. And if it were moving, it would move up towards the semicircle side. And the cold air mass is here to the north, behind the symbol. And if it were to move, it would move south in the direction of the triangles. So stationary, they're just hanging out. They're not moving one way or another. And because of the stationary aspect, there's no mixing of air. There's no there's not as much air pockets ascending like we talked about earlier, causing the precipitation, potentially nasty convective situation that you can get with a cold front overtaking warm air mass or warm overtaking cold. But you can be sure, and I put these notes on this slide because this is like an exact question in the written test. You can be sure that when a front passes, you're going to get a temperature change. That will happen. you're going to get a change in pressure, and it goes down and then up, and then you're going to get a shift in wind speed and typically direction. You can always see that when a front passes. By the way, this will be great for you because you're going to be flying out of Sugarland, which has I think one north-south runway. And whenever a front passes through, whenever like a cold front passes through, you'll know it because the wind will be like you'll have a great day for crosswind takeoffs and landings. The wind's no longer going to be up and down the runway. It's going to be like east-west, and you're going to have crosswinds all day long after a front passes. So remember those 3 points: temperature change, pressure change, and a wind change will all occur after you have a front pass through the area.
Okay.
Okay. So, and I'm just kind of reconnecting the dots here. So we've got, the sun causes the heating, which causes the pressure differentials, which causes the air movement. You've got Coriolis force, which screws up the air movement, which makes it unpredictable. You've got the pressure centers, which are created by the heating, the ununiform heating of Earth's surface. The pressure centers cause, large air masses to move around, and these large air masses have different characteristics, both in stability, moisture, temperature. And so that's what creates the weather systems, the fronts. So everything make good sense to you so far?
Mm-hmm.
Okay. Now, now that we've talked weather systems, I'm going to start breaking down some different elements of weather. The first one's going to be clouds. We're then going to talk about some aspects of weather like thunderstorms, wind shear, icing, stuff like that. Things that are, we're going from theory now to kind of application and definition, so to speak. But clouds, I kind of put this on here, but clouds are awesome because they're a good indicator of stability, number one. And they are a very good indicator of future weather. And by future, I mean like in the next couple or several hours. You can look outside. Say you're going flying at like 5 o'clock or 6 o'clock. You look outside around 1 or 2 at your office, and all you got to do is look at the clouds, and you can get a pretty good idea of what your flight's going to be like that day. Which is cool. It won't be your only source of information, but it's kind of cool just to look outside and know that you can get a couple indicators just by looking at the clouds. We talked earlier, cloud formation occurs because air rises. Air is heated up by the sun, and it rises. And as air rises, temperature decreases. And as temperature decreases, it hits the dew point for that particular atmosphere, and it condenses. And as soon as it condenses, it becomes visible. If it condenses to a certain point, it becomes rain, but we're not talking that just yet. But just in essence, the 2 ingredients for a cloud: moisture and temperature at or near the dew point. And then we're gonna get really comfortable with two terms: cumulus and stratus. And I know, you've probably heard these terms before. Cumulus are the puffy clouds, stratus are the smooth, gray, kind of fuzzy looking clouds. But it's these two particular families that are the general indicator of atmospheric stability. And clouds are put into these different categories based on altitude and stability type. And they are, from a definition perspective, something that you're going to need to know for the written test and potentially the flight test. But it's also just, this is good stuff to know when you're doing your flight planning. So you'll see when we look at the different families, the cumulus prefix and the stratus prefix or suffix. And then you've got these altitude designations, low, middle, and high. Now, if you remember, cumulus and stratus, I mentioned before, are an indicator, general indicator of stability. And I am gonna define it in a little bit here, but I'm just gonna go right off the bat and tell you that cumulus is an unstable atmosphere cloud family, and stratus is a stable atmosphere cloud family. And you can see in each altitude level, you've got kind of a combination of these unstable and stable families. Here's your cumulus at the low level. Here's your stratus at the low level. Okay, here's another stratus. Here's your cumulus at the middle level and your stratus at the middle level. And then you've got your stratus at the high level, cumulus at the high level. Okay, and so at each level, you've got these, designator prefixes, and to kind of, give you an idea of where they're at. Like the middle clouds are alto, 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 alto stratus, alto cumulus. The high clouds have a cirrus prefix, cirro, cirro, then cirrus. But the important thing to know about the cloud families is stability. So your stratus are going to be stable. Your cumulus are going to be unstable. Unstable, stable. Okay. And so just kind of tie in some concepts together real quick. Take, for instance, this nimbostratus cloud, which in this diagram shows that it's raining. The reason for that is a stratus cloud at low altitude that is precipitating is called just that, a nimbostratus. But can you venture a guess as to which kind of frontal system the nimbostratus might be associated with?
I'm going to guess so I know you said there was one more common than the other. It's the cold front pushing the warm air.
Mm-hmm. Yeah. And remember, cold frontal activity, because it's replacing hot air, warm air, is always indicative of very unstable atmosphere. Mm-hmm. So whenever you're talking unstable, we're talking cumulus. So anytime you have a cold front moving through the area, the blue line with the triangles, you're always going to have cumulus cloud activity, cumulus. So a nimbostratus would be typically a warm front cloud family, because it's stratus. It's associated with stable atmosphere, which a warm front is. Front is, yeah. Mm-hmm.
All right. So a cumulonimbus is more likely to be associated with a cold front, whereas a nimbostratus, because it's stable, is most likely associated with a warm front.
Exactly. Let me go back here real quick just to complete the thought. Here's our warm front diagram.
Yeah, I misremembered this one, to be honest.
Yeah, no, not a big deal. So the reason a warm front is typically a more stable atmosphere is because the cooler air is being replaced. It doesn't want to rise. Okay? The warm air is moving and it's going to rise. So it's moving up this ramp here. It's going to rise. And it's pretty, I mean, if you were to like study it, it's very benign, right? It's like even this angle here is extremely aggressive. Like for instance, this might be Houston, and this might be like, Dallas, and this might, so it's like that ramp is significantly benign. And so even the warm air moving up this ramp isn't that significant, right? It's not going to cause a convective type unstable atmosphere. As opposed to the cold front, where you've got this warm air just waiting. It's just the warm air sitting here just waiting for some reason to rise. It just needs that force to push it up.
Yeah, that makes sense. I remember that now. Okay.
Mm-hmm. So So hence the reason the clouds are kind of classified the way they are. And then you picked out, you said it right on, 100% correct. The cumulonimbus has the cumulus prefix, and so it is an unstable cloud family, and is the type of clouds that you see for thunderstorms. It's the stratocumulus and the altostratus cloud families eventually become a cumulonimbus cloud if there is enough moisture and vertical development in the atmosphere. And well, by vertical development I mean instability or stability.
So stratus is stability, cumulus is instability.
You got it. That is dead on.
Okay. And cirrus is just like high ice crystal clouds, right?
Man, someone's been reading. Listen to you.
I've watched some weather stuff, but I'm still taking it in. So this is still very helpful.
No, you're spot on. Cirrus is a frozen ice crystal. It is a condensed ice crystal at high altitude, above 20,000 feet, typically. So, all right. So those are cloud families. You do want to get to know them, but if there's anything you want to memorize right here, right now, it's that stability family, cumulus versus stratus.
So one of the other ones is, and that was on the, I guess 2 or 3 slides back, the towering, right? So there's, remember correctly, there's the cirrus, the alto, the cloud, the towering. There was one other. No, the one with the ramp.
Right there.
No. The one that you were referencing just a minute ago, where it was showing the stratus formation, the stratonimbus.
This one right here.
Yeah, the opposite of that one, where it's the warm front pushing the cold. Yeah, I thought there was one called a tower. Maybe it was back. Okay, never mind.
Well, so no, you're right on. So the towering cumulus is the initial stages of a thunderstorm.
Okay, maybe we haven't gotten there yet. Then that makes sense.
Well, no, you're spot on. So in a cold front scenario where you've got this warm air that is kind of hanging out, just waiting for a reason to get kicked up, right? To get risen.
Mm-hmm.
Remember, cold front equals unstable atmosphere. Warm air rises, creates cumulus clouds, because remember, cumulus is unstable, right?
Yes.
And so cumulus turns into towering cumulus after the atmosphere has risen, has brought that air up, right? And then towering cumulus becomes cumulonimbus.
Okay.
And that occurs typically, I mean, don't get me wrong, that scenario can happen in a warm front, but it is not typical.
Got it.
Yeah, that is a cold front phenomenon by far. Okay. So just kind of, I'm going to back up and do some qualitative type discussion here, because, at the end of the day, theory is great, but we want to know what it means to us when we're flying the airplane. Plus, some of these pointers are on the written test. So as far as stability goes in clouds, and I am rehashing a bit here, so apologize, but moist, stable air is characterized by stratus clouds. We talked about that. Steady precipitation, meaning like, your rainy day, and little or zero turbulence, like very smooth flying. So that is moist, stable atmosphere. Stratus, rainy day, like you wake up, it's raining all day. You go to bed, it's raining, that type of thing.
Yeah.
And then no turbulence, as opposed to a moist, unstable atmosphere, cumulus clouds, big puffy cumulus clouds, showery precipitation, meaning like, it's raining on the street next to you, but it's like the sun's shining on your street type thing.
Yeah.
And then like extreme turbulence, like don't fly turbulence. So, yeah, and it's important for the written test. It's important. Actually, wish someone had told me this back when I was taking the written test. It's important to know the difference between showery precipitation and steady precipitation, because the FAA and the study guides, they do not, I mean, they don't do a great job of talking those two things. You know, one is like the rainy day. You could drive 1,000 miles and it's foggy and raining. And then showery is like you're driving on the highway and you can see like 20 miles in the distance, like a rain shaft, you know? So does that, all that make sense to you?
It does.
Okay, cool. Okay, so as you might expect, if you've got an inquisitive mind, given the fact that temperature decreases with altitude, and as an air mass moves up and temperature decreases, it eventually hits the dew point and condenses into a cloud. Given that fact, you might be wondering, hey, can I calculate the height of a cloud if I know what the temperature and the dew point are? And you would be 100% correct. And I put this on here because it is a math equation, or it's a calculation you have to be able to demonstrate for your test. And the test questions, now your instructor and your examiner may ask you to demonstrate this in a stable atmosphere, but the written test, as far as I can tell with the study guide that I have, only requires you to do it for a unstable atmosphere. So there's that 4.4 degrees, right? This is the convective lapse rate. Anytime you see the word convective, instantly you think unstable. So, to solve this problem, we have to know what lapse rate we're using. Do we have a stable or an unstable atmosphere? Obviously, you need to have your temperature, right? You need to know your temperature and your dew point. And then you just do some math. So this one, for a math whiz like yourself, should be pretty easy. But I have an example here just to kind of get us to get us acquainted. So temperature at the surface, 70 degrees, dew point 61 degrees. For the test questions, and for any time you're asked to demonstrate this, just kind of assume that dew point's constant, even though in a real atmosphere it's not. But dew point does not change radically like temperature does. But we're going to assume that dew point's constant, 61 degrees. And we need to find the altitude of that cloud. So what's our difference? 9 degrees, right? 70 minus 61. And so if we assume a convective or unstable atmosphere, which means we got to use a convective lapse rate. So assuming 4.4 degrees Fahrenheit per 1,000 feet of temperature drop, all we do is take our 9 divided by 4.4 and multiply by that per 1,000 factor. And the cloud bases, so where the cloud starts to form, is going to be 2,000 feet in this example. So from what I can tell, the study guide, the FAA test bank, has, I think, like 5 or 6 questions that require you to find the base of the convective clouds.
Can't you also, you can also calculate the top with some information as well, right? If you know what the cooling rate is.
Oh yeah, I'm sure there's some math that you could do to perform that. I guess, just thinking out loud, I guess the challenge there becomes the speed at which the air is moving, which of course affects this answer right here too, obviously. But once you reach the point where you've got towering cumulus, and again, I'm just speaking out loud. I really don't know the answer to your question, but once you have towering cumulus where the base is at 2,000 and the top is at like 25,000, so you've got like a 23,000 foot thick cloud. I bet the math gets a little fuzzy if you tried to calculate something there. I'm not sure what would affect that. You know what I mean?
I think the video I saw showed that if you know what the temperatures were at each altitude, and you knew that I think it was with adiabatic situation, you could determine when the temperatures would equalize, if they would equalize. So I think it was a situation where you knew a lot more information than just the convective lapse rate. Anyway,
Yeah,
I don't want to derail. I think I was just trying to remember the video. Anyway,
yeah,
it's okay.
maybe so. I've actually got a cool tool, and I'm just going to show it because it's cool. That is kind of used for instrument flying to show. Let's see if this works. To show cloud bases and cloud tops. Maybe not. I know this site's been acting funny lately. How do we do it? Okay. Anyway, oh, here we go. Okay. So what this is, and without going into like major detail, it's a comparison of temperature and dew point on a logarithmic scale. So you can try to attempt and determine what level the clouds are at. When the blue line and the red line converge, the temperature and the dew point are equal. So you can see kind of up here in this little throat, they're not converging necessarily, but they're close. So you can guesstimate that if you run into clouds, it'll be at this level, which on this chart is 4763 feet, 4763 next to my cursor. So yeah, if you've got any free time and you want to geek out a little bit, look up what they call skew T diagrams.
Okay.
And it's a comparison of temperature and dew point. Show you where the clouds are. This also says that there'd be clouds up here where they converge at 26,000 feet. So, so anyway, so that's the standard equation you got to know for the written test. Just temperature dew point differential divided by the lapse rate that you choose. For the written test, it's probably definitely going to be 4.4 degrees per 1,000 feet.
Okay.
So, and then. Talking about just some more application, the theory, we've gotten past the theory now. We understand about air movement and pressure centers and fronts, weather systems and fronts. So what does it mean to the pilot? What does it mean to the flight planning? Quite honestly, in our type of flying, it typically determines whether we go or we don't go sometimes, right? Depending on how severe the weather is. So we'll talk about some piloting aviation weather considerations, and how it relates to what you're going to run into in the real world. I mean, like literally real world. When's your first flight lesson? Like next week, next Saturday?
August 26th.
Yeah. I mean, you're going to use this information like next Saturday. It's freaking great. So turbulence. We have talked a great deal about stable versus unstable atmospheres. And if you want to associate turbulence back to one of the fundamental, connect it back to a fundamental weather theory, this is all about stability. So if you've got a stable atmosphere, perhaps you're flying in the vicinity of a warm front, or maybe you're not around any front, maybe you're just in a high pressure area, you're gonna have very stable atmosphere, and you're gonna have like no turbulence. Your flight will be extremely smooth. You might not even feel a bump. But once you get atmospheric instability of any kind, your ride is going to be bumpy, and it's in the vicinity of a low pressure center or a cold front, or convective lapse rate. ForeFlight actually has a pretty cool tool. Did you, by the way, did you download ForeFlight yet?
Oh yeah.
Mm-hmm. Someday go into it. Go into a look up an airport. Type in like Sugarland or something like that, and go to weather and scroll down to the winds and temperatures aloft report.
Okay.
And ForeFlight will actually warn you in the report if there's an unstable atmosphere based on the temperature change with altitude. So every time I open up ForeFlight, if I see, it says warning, unstable atmosphere or whatever, I'm like, oh shit, it's gonna be a bumpy ride. So and this is totally rehashing, but I feel like we should just for the exercise. Unstable atmosphere, cumuliform clouds, large temperature lapse rate, so large change with altitude, cold front passage will cause atmospheric instability. And then, so when you're flying, and shoot, you may even encounter this on your first. If you tell your instructor you're comfortable with flying in a little bit of turbulence, you may get some. What do you have to keep in mind when you're operating your aircraft as far as airspeed goes?
That turbulence, you're going to back down the speed.
Mm-hmm.
You're going to definitely stay out of your caution range and stay below VA.
Hey, man, look at you, rock and roll. That is exactly right. And then, if you're with passengers who maybe don't fly much, obviously that's a huge consideration. One thing that people kind of take for granted just a little bit is when you get your private pilot's license. I mean, that gives you the authority to take people with you that may never have flown in a small plane before. So that's a huge consideration. And then level flight attitude. And I put this in here specifically because this is a written test question on the FAA test. I think the question is something to the effect of, if you're in an unstable atmosphere with turbulence, what is one thing, how do you want to fly your plane? And, there's a couple answers that sound right, but the only right answer is with a level flight attitude. And it's actually a pretty good point because, can you remember back when we talked about aerodynamics, what happens when you bank the aircraft?
You increase your G's.
Yeah, exactly.
Which also
loading.
Yeah, you're loading the airframe and you increase the stall speed.
Right. So if you assuming you go into a 30-degree bank, which I think, don't quote me off memory, I think it's like 1.5 G's or something like that. And you're turning and you hit turbulence. Well, the turbulence is just going to add to your acceleration, to your G loading. And if your airplane is a Cessna 172, which is actually only designed to handle 3.8 Gs in any direction, then, I mean, you could easily overload your aircraft very quickly.
Isn't it also 4.4 or 4.5 in utility mode?
That's right. Yep. If you've got a utility aircraft, 4.4, that's the number. Man, okay. Alan, you've been freaking reading. Listen to you.
Dude, it's really important to me that I do this, so I'm just taking it very, very seriously.
Okay. No, I'm like literally, that's awesome. I'm very excited. I mean that is like a very minor detail to remember from your reading, given the fact that you're this is a lot of information, right? So that's awesome.
It's a lot of information.
Okay. Thunderstorms. So turbulence and thunderstorms, they go kind of hand in hand. One obviously causes the other. And again, thunderstorms, unstable atmosphere, it's the same deal. So there are 3 specific requirements for a thunderstorm, and all 3 have to be there. It can't be like 2 and a little bit of 1, or a lot of 1 and a little bit of 2. It's like all 3 have to be there for real. You've got to have sufficient moisture. So your humidity has to be just right. You have to have an unstable lapse rate, meaning 4.4 or greater. And you have to have a lifting mechanism. And when I say lifting mechanism, that means atmospheric lifting, air pocket lifting. So what causes that? Temperature change, right? The air heats up. Frontal passage, a cold front pushes or plows its way through a warm front, causing the air to lift. Terrain also causes this. If the winds are favorable around a mountain and the air lifts its way up a mountain slope, that will cause thunderstorm development as well. So those 3 items are critical to create a thunderstorm. And what's great is here in Texas, and I can't say that this was the case when I lived in Philadelphia. It definitely was not the case at all in Southern California, because Southern California never rained, right? But in Texas, you can witness this weather phenomenon almost every freaking day in certain parts of the year. You wake up, it's muggy out, the humidity is the relative humidity is high. Throughout the day, the sun heats the heck out of the surface and the air, starts to rise, pretty soon you start seeing these cumulus clouds. You know what I'm talking about? These big puffy clouds. Yeah. Right. So because the clouds is an indication of your lifting mechanism, it means that pockets of air are getting lifted significant heights, significant altitudes. The only way that it's going to continue lifting is if there's an unstable lapse rate, which indicates an unstable atmosphere. So you can watch this process take place in Texas like every day. And you're in an interesting spot because you got the Gulf of Mexico feeding moisture into your region like daily.
Yes, we do get a lot of sort of weekday and weekend short-term thunderstorms as the year changes.
Yep. So the thunderstorm also has 3 stages. Do you happen to know what they are just off the venture guess?
Cumulus, mature, and dissipating.
Man, you are just rocking all over the place. Rocking. That is awesome. Do you, I mean, for 1,000 points, can you tell me like what the characteristics of each stage?
Sure. So in a cumulus, you're going to experience updraft. In a mature, you're going to experience updraft and downdraft. And then a dissipating, you're going to experience downdraft.
Wow. What is I'm having fun with this. What is the sign that if you're flying your airplane through a thunderstorm, God forbid, and what is the sign that you've reached the mature stage?
You might see a wall cloud.
Okay. Anything else?
I want to say like precipitation, but I don't know that's for sure.
Yeah, that's right. That's exactly spot on. And that's how it's going to be presented to you in the written test.
Okay.
Yep. Once you start seeing the rain, that is the mature stage.
Yeah, this stuff is really fascinating. Like I agree with your sort of geek out nature with it. It's just fascinating how it all comes together.
Oh, weather. I almost wish I would have studied meteorology. I mean, weather's freaking awesome.
And you could have been paid for being wrong half the time.
That's right. You don't even have to be right at all. Not even close. So when you read up and studied on thunderstorms, did you also determine, or did it tell you what the 2 types were?
I didn't get that far.
Okay. So there's 2, I'll call it generic types. Sometimes they are kind of mixed, right? It's like one and or the other. But the first type is what we call isolated or steady state. I think steady state's actually the official term. But when you watch the news at night, they usually use the term isolated thunderstorms. And hey, what do you know? There's Houston. Isolated steady state thunderstorms can be identified by looking at the radar screen, the weather radar, and thunderstorms just kind of pop up like out of nowhere. Like all of a sudden, clear blue skies turns into like a huge freaking radar return, like out of nowhere. And the second thing that can help you identify it is they occur outside of outside of any frontal activity. So there's typically, it's not always the case, but typically there's never any sort of frontal activity taking place. It's just it's hot, there's moisture, and the air's rising, and that's what causes it. There's no front helping the lifting. There's none of that. It's just happening right there in place.
So when you say that, does that mean that it could be like a low pressure system without it being a front?
Yeah. Typically, that's what it is. You've got a major low pressure system in a certain area that's dominating. Sometimes you hear the weatherman say, "Oh, the pressure system's dominating," meaning it's not letting any other fronts kind of move in its space. And to your point, it is along with the vertical movement of the air. You've got the appropriate amount of moisture, and you've got the unstable lapse rate, which causes your unstable atmosphere. And so all of a sudden you'll just have these thunderstorms just pop up out of nowhere. It happens in Florida like all the time. I think it happens down towards you guys quite a bit too. Now, the opposite side of the coin, complete opposite type of thunderstorm, is what's called a frontal thunderstorm. Sometimes you hear it termed squall line. And truly, these thunderstorms are exactly what we talked about, I mean, in this graphic way back here. This right here is a squall line graphic where you've got a front moving the air and causing this phenomenon right here, causing this unstable atmosphere thunderstorm.
I did get into squalls a little bit in my reading. And
okay, good. Yeah. So I put this little graphic here. 9 times out of 10, especially in Texas, I want to say in Texas, you can almost guarantee 10 times out of 10, a squall line will be caused by a cold front frontal system moving through across the state. In fact, last night we had some frontal thunderstorms move through Dallas area from a front moving through. So the other thing just to note, in case your instructor talks about it or the examiner, the weather always kind of occurs ahead of the front. So I put this little front line here strategically. Your weather isn't like happening necessarily right on the front line. It tends to happen kind of in front of it. We've got a good amount of time here. I just want to show that if I can. It's interesting. So I'm just pulling up Wonderground. We're going to go to radar. We're going to check out the radar, point out different kinds of thunderstorms, and then I'll compare them to where the frontal boundaries are. We can see if any of it makes sense. So let's zoom out here. Then I'm going to put the fronts on the screen. Okay, so here's kind of this is a loose. It's not a squall line by any means. It's kind of weak in its organization, but this would be a frontal thunderstorm system here, stretching from Memphis up to Cincinnati, and you can see how it's several hundred miles in front of the actual front, right?
Yeah,
that's what you'll typically find. That it's not. I can't say in Texas I see them that far ahead of the front, but just depending on the conditions, it could be. And then here is. This is kind of your classic warm front weather pattern right here. You've got your warm front. You do have some thunderstorms, so it looks like the atmosphere is just right to create some instability. But by and large, I mean, look at some of these. Look at this radar. It's mostly green, right? It's mostly just rain showers. Most likely characterized by stratus, nimbostratus. Stable atmosphere clouds and that kind of thing. And then you've got your occlusion, your cold front occlusion up here. There's your purple line.
And just to refresh, the direction of movement is the opposite side of the symbols or the side of the symbols?
So the direction of movement is in the direction of the symbols.
Okay, so that would be saying moving to the southeast.
That's right, exactly.
Okay.
The air mass that the symbol characterizes, like the cold air mass in this case, is to the flat side of the line. So it's behind it. Yeah. Mm-hmm.
Okay, cool.
Yep. And then over Texas here, we've got a stationary front. It's not really wanting to go anywhere. And so it's kind of just hanging out. And actually, this front has been hanging out for like 3 days. Just been chilling out. It's going to be just kind of reaching back to some of the theory we talked about. It's going to be influenced by other pressure centers, right? It's going to be influenced by these high pressure centers because, like we talked about before, the high pressure centers tend to be a divergent air mass, meaning, starts high, sinks, diverges, pushes some of the weather around outside. So these high pressure centers are absolutely going to make their way down towards us and push this front through, push this weather system through. So yeah, you could spend a lot of time looking at a map like this, but just know, you've got your not quite squall line, but frontal system here. And then, I would also argue that the weather we're experiencing in Texas today is also frontal, just because you've got this cold front here. It's not encroaching because it's stationary, but it has caused some of this warm air to rise, causing these thunderstorms. So.
Okay.
Okay. All right. So turbulence, thunderstorms. Thunderstorms cause turbulence. If your instructor wants to quiz you and ask you, how close should you get to a thunderstorm, you should tell them it's a trick question, that you shouldn't get close at all, right? And that's because of the turbulence and notably wind shear. Wind shear is a byproduct of a thunderstorm. However, it can also be the byproduct of just pressure centers doing, different air movements throughout the atmosphere. I think you've probably heard of the term clear air turbulence, right?
No, actually, I don't know. I haven't heard that term. I probably know what it is, but maybe not by name.
Well, clear air turbulence is a type of turbulence that is not caused by a weather center necessarily, like a thunderstorm or a frontal activity. But clear air turbulence is just caused by pockets of, I'll call it, just aggressively moving air in the atmosphere. Like remember that pictorial I had before where you had the low pressure center next to the high?
Yes.
That would be an extremely chaotic wind atmosphere. Just because you've got the low pressure system sucking air up, right? The high pressure system replacing it, that kind of thing. But wind shear, and that's clear air turbulence. That goes with the wind shear discussion. But wind shear, by definition, is a sudden change in wind direction and/or, but typically it's and speed, and it can occur anywhere. Where you're going to want to, from an application perspective, worry about it the most is around weather systems, thunderstorms, notably thunderstorms. If you are flying back to the airport after a cross country and a thunderstorm or a system has just moved through the area, this is the one thing you're going to have your ears perked up for is, any pilot reports of wind shear going on because of the frontal system or the weather that just moved through. So I'm going to illustrate just a couple different kinds of wind shear that you want to think about when you're flying the airplane. And I'm going to talk about it in reference to approach to landing. Although it can happen in any phase of flight, obviously, but approach to landing happens to be a pretty critical phase of flight because you're at a low airspeed. You're kind of configured to, stall the airplane right above the surface of the runway, right? So in this example, we've got a headwind, and our Boeing 777 that we're flying is on final approach to the runway, let's say, 3 miles out, maybe something like that. And we're flying, and we've got a headwind. Why? Because we always take off and land
into the wind.
Into the wind, you got it. Yep. And we all of a sudden hit what's called a head wind shear or a headwind shear, or sometimes people say the wind sheared in the head direction. So what this means is my let's call it 10 knot headwind just sheared to like a 60 knot headwind. Like it just, I've got all sorts of headwind right now. So right off the bat, if my true airspeed was, say approach speed, and I got a head wind shear, what would that do to my true airspeed?
It would reduce it.
True airspeed.
It would your true airspeed.
Yes, it would.
It would increase your indicated airspeed, but it would reduce your true airspeed, right?
Remember, true airspeed is the speed of your aircraft in the relative air, which has to include the wind, right? So you're right about the indicated, but it would also increase your true. There is a type of airspeed it would decrease though.
Ground.
Yes, it would decrease your ground speed. Correct.
Okay.
Yep. So you got
so that.
Yep. So that's that, right? So true airspeed increases, ground speed decreases. So you're now approaching the runway at a slower speed, physically over the ground. But what's your thoughts on like airplane performance? What do you think the airplane's going to do?
I think it's going to want to fly better. It just got really good airflow over the wings. The thing that I was thinking about is if you're on approach, your flaps might be down. That could seriously jack your plane.
Oh yeah, no, absolutely. Yeah, your airplane's going to perform amazingly. It's going to climb, right?
Yeah.
Yeah, it's going to take back off essentially. And as you're flying the airplane, what you're going to notice is it's going to increase altitude without you having to push or without you having to pull the nose up. Like, usually if you want to increase altitude at a constant airspeed, you got to pull back on the stick, right?
Mm-hmm.
Well, not in a wind shear event. Like literally your altimeter will jump up 500 feet and you could be like in a nosedive. Like you wouldn't have to have your nose up.
Wow.
It's nuts. Yeah, it's pretty amazing actually. But the reason I want to bring this up is because a lot of pilots, when that happens, they pull their power, right? They're like, oh shit, I'm climbing, I got to pull my power.
Mm.
Well, the problem with that is the shear goes away, right? That's not a constant wind event.
Then you have no power.
Exactly. So now your true airspeed goes down closer to your ground speed, which has just been severely affected by that shear.
And you stall the plane.
You stall the plane
pretty easily.
Yeah, you stall the plane, exactly. That's right. So that's one kind, and then the second kind that we have to concern ourselves with is obviously the opposite, right?
Yes.
And this one's kind of funky too, the tailwind shear. So again, true airspeed and the tailwind shear is going to
go down.
Right. Yeah, your relative motion in the air is going to reduce, but your ground speed's going to go up, right?
Right, because you're pushing the plane.
Mm-hmm. The problem is the airplane itself doesn't really care how fast you're traveling over the ground because you're not a car. So if the shear is bad enough, what do you think the airplane's going to do?
Sorry, I missed the first part of that question. My head jack pulled out as I shifted.
No, you're good. So like you said correctly, your ground speed goes up, but your airplane, it doesn't care about ground speed because it's not a car. So what do you think in this event? How do you think the airplane's gonna be?
It's going to decrease flight performance. It's going to disrupt the airflow over the wings.
Oh yeah, and if it's bad enough, it'll stall.
Yeah.
Right. If your true airspeed drops below stall speed, you're relatively screwed. But just like in the prior example, I mean, the shear eventually goes away at some point, and you'll regain performance. But if it's bad enough, you could be in a pretty sticky situation.
Right.
So, and what a lot of pilots make a mistake of is pull back on the stick, right? All of a sudden you start losing altitude and you're like, oh shit, I got to pull back on the stick. And then you just induce the stall at that point.
Would you instead increase power or would you just ride it out?
Yep. Increase power and push the nose down.
Okay.
Yep. It's the push the nose down part is extremely counterintuitive because you're losing altitude, right?
Yeah, but if by pitching down you increase airflow over the wings, so that's one thing I've had beat into me through discussions with you and watching a lot of like air disaster shows is, obviously don't nosedive into the ground, but in that situation, if you're looking at a stall, pitch down, like gain altitude by gravity.
That's right.
Gain airspeed by gravity.
Right. Yep. Just increase your kinetic energy, right?
Yeah.
So that's spot on. So I said before, this can happen anywhere, and it truly is good to just be mindful of wind shear at any point. Obviously, if you're in cruise altitude and you have wind shear, it's not as bad because you have plenty of altitude to recover from a shear event. But there are areas that you want to focus on, like thunderstorms. You're never going to fly near a thunderstorm, God forbid. But if you did, you would worry about wind shear because there's to your earlier point, during the dissipating phase, there's a lot of downdrafts, right?
Mm-hmm.
That causes high wind situations and wind shear. Frontal zones, jet streams. I put clear air turbulence. That's pretty typical around a jet stream. Now, you and I don't fly around jet streams yet. That's a high altitude thing.
Yeah, a little bit.
Yeah, but here's one thing that you want to. Here's one thing that's not totally intuitive that does show up on the written test. Wind shear can be found, and you should be aware of it in low altitude temperature inversions with high winds. So you remember temperature inversion was when you've got
cold to warm to cold, or other way around. Warm,
exactly
cold,
right.
warm.
Yeah. So if you look at the weather report at the airport before you go flying, and you're like, oh my gosh, you got some pretty high surface winds, and some high winds aloft, and there's a temperature inversion, pretty good chance you're going to see some changing wind direction and speed. And then just a couple pointers. I mean, thunderstorms. I am the biggest. I am the biggest scaredy cat of thunderstorms, and you get more and more comfortable. I mean, maybe that's the wrong term to use. You get smarter as you fly more about thunderstorms. But yeah, you just 20 nautical miles. I multiply that by 2. 40 nautical miles. Just don't even deal with it. And then we're going to talk about pilot reports, PIREPs. Those are very handy when discussing wind shear events, because when airplanes come into land and they experience a wind shear event, every pilot is encouraged to kind of notify air traffic control. Hey, just landed at Sugarland. We experienced a major tailwind shear event, and then they'll put that. They'll publish that so people can see it. So we'll talk about that during the next session.
Okay.
All right, doing pretty good on time here. Icing. So it's kind of funny, all the weather phenomenon that thunderstorms create. Icing is another phenomenon that occurs within thunderstorms. Of course, we're never going to find that out because we're never going to fly through one. But icing does also occur in stable atmosphere as well. So it's important to know about. Nimbostratus, remember that high moisture precipitation cloud in a stable atmosphere? That is a significant icing cloud. High moisture content, visible moisture. It might be snowing, sleeting, but icing is of interest because your airplane cannot perform if it's covered in ice. There's a couple reasons for that. You want to venture a guess?
2 that come to mind. One, because it could disrupt the airflow over the wing and wreak havoc on the pressure differentials from Bernoulli's principle. And the second would be the weight that it would form.
Yep, that's exactly spot on. The weight is big. The airflow disruption is huge. I mean, it doesn't even take a quarter of an inch of ice to cause a huge airflow disruption. But from a weather theory perspective, there's 2 things that need to like raise your eyebrow when you're looking at weather reports. Visible moisture. So that means you're flying through a cloud, cloud of visible moisture, and the ambient temperature. Well, I would say more accurately, the aircraft surface temperature is below freezing, which typically that means the ambient temperature is somewhere in the vicinity, so to speak. So if you're below 32 degrees Fahrenheit and you're in visible moisture, it is fair game for aircraft icing. And what's nice about Texas is we don't typically have to worry about this. I mean, the winter time is one thing. It does get cold in the winter time, so there is some consideration you have to keep in mind. But when you start doing some flying up in the north, there's like weeks and weeks and months where I couldn't go flying because the temperature was freezing all the way down to the surface and below freezing at the surface. So here in Texas, we have it pretty good. The fact that we can enjoy some relatively mild conditions in the wintertime. But icing is something that is to be avoided, just like thunderstorms, because you can consider this scenario. You're flying in the north in the wintertime. You enter a nimbostratus cloud where there's snow and sleet, so you've got visible moisture, and it's below 32 degrees, so it's below freezing, which is the proper ingredients, and your aircraft starts picking up ice. Okay, well, you realize this and you're like, holy crap, I got to get out of this. So you decrease your altitude, you get out of the visible moisture, because that's kind of your first action, right? Leave the visible moisture. But then you realize that, oh shit, every airport in the surrounding 100 miles is all below freezing. So what does that mean?
Say that again.
So your aircraft picked up ice, right? Because you flew through a cloud.
Yep.
So you get out of the cloud to stop picking up ice, and we're in the north and it's wintertime. But then you realize that all the airports that are around you that you can land at, because you now have like an emergency situation, are all below freezing. So what does that mean?
You're in a really bad problem.
Yeah, exactly. It means that the ice is never going to melt.
Yeah, like that's what I was thinking. You could never shed it and you can't land.
Yeah. So if your aircraft is severely crippled, then that's what you've got all the way to the ground. There's no way for your aircraft to lose that ice until you put a heater on it. So, I mean, you just have to be careful. And then there's a couple pointers that you want to remember. You just, in the wintertime, it becomes habitual. You always look at temperatures. You always know what your freezing level is in the wintertime. Here in Texas, it ranges between 3,000 and 6,000 feet freezing level. In the summertime, it's like 16, 20,000. It's really up there. And again, you may run into a situation where you're not able to melt the ice off. So you just have to know that sometimes you're in it to win it. And if you got to land your airplane, just keep in mind that if it's heavier and if the airfoil is screwed up, just got to remember back to your aerodynamics fundamentals. You're going to have to increase true airspeed for every phase of flight. So approach, landing, you're not going to be approaching and landing at the same airspeed if your aircraft's covered in ice. So that's so those are some, I'll call it, fundamental terrible weather flying applications: thunderstorms, turbulence, wind shear, ice. And since you're going for it and getting your instrument rating relatively quickly after you get certificated, ice is definitely something that you'll become well schooled in. Oddly enough, and maybe this is a good thing, ice is something not a lot of people have experience with. So I certainly don't. I don't think I've ever picked up ice. So maybe that's just good flight planning, but who knows? Okay, we've got about 5 more minutes. I've got a section on fog here, but I think it's a relatively long section, so I think I'm gonna hold it until next class, if that's cool with you. Unless you want to go over a few minutes, I'm good either way.
So I did start getting into fog a little bit on one of the videos I was watching. So actually what I'd rather do for a few minutes is review the question that you had, because I keep getting myself into confusion states with this. So instead of running super long, maybe we could just circle back on that, because I actually have a response that I'm like, I don't even think that's right, because I know it's high to low, look out below.
Right.
And I figured it would be the reverse in the opposite direction, but I'm not convinced. And I psyched myself out and I started doing some math. And so now I'm just confused.
Yeah, no. That's fine. I'll be honest with you. It's like this question is, I don't think there's a question exactly written like this on the written test. And it's one of those things that you won't necessarily use an application, right? But you might, and it's always good to kind of understand the different directions of pressure. So what I like to do is I like to think about it in terms of how the altimeter works, right?
Mm-hmm.
So as I'm flying from an area of low pressure to high pressure, if I stay at a constant, call it absolute altitude, meaning I'm not compensating. I'm not compensating my physical altitude for the change in pressure. Then as the pressure increases, my altimeter thinks I'm going down.
Yeah.
Okay. Yeah, go ahead.
I'll tell you where I got confused. It's because I've been recently getting into the oh, no. Nope, I take that back. Nope, keep going.
Okay, yeah. Um, so yeah, so I try to think it in terms of what the altimeter thinks, knowing that the altimeter is um, going to go up as pressure decreases. Even I had to think about it. And it's going to go down as pressure increases. And the reason for that, as we know, is because as you go down towards the surface, there's more air mass pushing down higher pressure. So in this example, low pressure to high pressure. And so as I maintain a constant absolute altitude above the ground, my altimeter going to high pressure thinks I'm going down. It thinks I am decreasing in altitude.
Right, so it thinks you're lower than you actually are.
Exactly.
So it is the
Right.
antithesis of it. Okay, that's what I thought.
Yep. Yeah. So if you do maintain a constant absolute altitude, your absolute altitude is going to be higher than your altimeter says you are.
Okay.
Yep.
So
And
okay, so I'm definitely wrong there. So this, yeah, okay.
well, yeah, no, and be honest with you, it's a complex mind trick, right? It's you did get I think you did get the math right though, as far as the 1 inch per 1,000 feet, right?
Mm. Well, this was just a formula I found in doing some Googling that it's sort of a common rule of thumb is you could use this. I don't think this is a super accurate approach. I think this is one that you could just do quickly.
Okay.
So I found that.
Okay. Well, let me real quick. I'll create a new slide here. Let me just go through the math real quick. And so what's important to know these types of problems is that 1 inch of mercury, and I think you mentioned this earlier, right? Is 1,000 feet,
Yes.
right? So all we got to do is find the difference between the altimeter settings and use the 1,000-foot calculation. So what did I say? 29er, 83, and 3032. So let's see, 3032, 29er, 83. So I've got a difference of 0.49. Okay.
Mm-hmm.
If I multiply that by 1,000, I've got 490 feet of difference, and then at this point all we have to do is apply in which direction. Low pressure to high pressure means your altimeter thinks you're going to be lower than you actually are, so you actually are higher by 490 feet. So your real altitude is 490 plus field elevation.
Okay. Can we do that one more time in terms of the sign?
Yes. So I'm going to actually draw it on the screen. Here, watch this. So here is the ground. Okay. And I'm going to steal my buddy, Boeing 777. Okay. Here is SGR. And here is OKC. And, obviously they are at different field elevations.
Mm-hmm.
But that doesn't matter because we're going to apply that in the equation, right? We're going to apply that field elevation in the equation. So the pressure here is, this is low pressure, right? And this is high pressure. I think that's what I did, right? High pressure. Yep. So as we're flying along, if we stay at a constant altitude, meaning my altitude's not going up or down, but it's constant, if we don't adjust our altimeter for the higher pressure setting, right?
Mm-hmm.
The altimeter, which is it's a sensitive barometer, is going to sense this higher pressure. And it's going to tell the pilot, hey, dude, you're going down. Why? Because pressure increases as you go down. So he's telling the pilot, the altimeter is telling the pilot, hey, dude, you're going down. You're at a lower altitude, But the aircraft actually hasn't gone down. Same altitude.
So in terms of so I get all that. So I was just thinking, when you did the difference, if you did the actual minus the origin, that sign kind of works itself out automatically. So if you were to do this in reverse, you would know that you were lower than your altimeter was saying you actually were, because no.
No, you're right. No, what you just said was right.
So, but the sign would be wrong. So you would no, okay. So if you did, it's almost like you need to reverse the sign, because what were the numbers again? It was like 30 point something.
Yeah, this was 29er 83, and this was 3032, I think.
So if you did the new minus the old, no, the old minus the new, that would give you your proper sign, right? So if you did the opposite direction, if you went from OKC to SGR, you would want to add it. It ended up being a negative number plus the field elevation, right?
If you did the SGR minus the OKC?
Yeah, so that would give you a negative 0.49. So it would think that was 490 feet. So your altimeter would think that you were, well, shit, this is where I get confused. So
yeah,
how would
you could do it that way. Yeah, I think so. Yeah.
So do you just always know that if you're going from low to high to add the difference, and if you're going from high to low to subtract the difference from the field elevation?
You could do it that way too. Yeah. You, from this point forward, you could just say, hey, if I'm flying to an area of higher pressure, then I'm higher than I actually think I am. Like I always add. You could do that.
Okay. How do you do it?
Well, unfortunately, I'm like, you and me are very similar. So I sit here and I think about the actual theory behind it. You know? And I'm thinking, well, how does the altimeter work? What does I have to think about it that way. I have to think, okay, hold one thing constant. I can hold my altitude constant. That's easy enough, right?
Oh, I see how you did it. Yeah, so if you're lower than you actually are, you know you need to correct up.
Yes.
Whereas if you're higher than if it's saying you're higher than you actually are, you need to correct down. That's what you're talking about in terms of the theory.
Yeah, that's right. Yeah.
Okay. Yeah, that's easier for me to wrap my head around, because there's no funky math trick to remember. It's you said the theory of it.
Well, and that's why let's go in the opposite direction real quick, just to kind of finish the point. That's why when they say when going from high to low, look out below, because when you're going from high pressure, like OKC, to low, and you're holding a constant altitude, your altimeter is actually going up, right? And so
gaining altitude.
To compensate for that, because you're a good pilot, you're gonna like do this. All right, I better hold my altitude, my indicated altitude, right?
Yeah.
So, yeah. So, hence the moniker. But yeah. So that's good stuff. Also be aware of what pressure and altitude do to the airspeed indicator. That's another one that always screwed me up. I swear. Even when I took my commercial written, always screwed me up. Airspeed indicator.
Okay.
So.
Give me a chance here. So if you're going from a low to a high, the pressure gets thicker, so it's think you're going faster?
Right. Yes. The gauge, if you're going from low to high, there's going to be a higher impact pressure coming into the pitot tube. So the airspeed indicator is going to think you're traveling faster, even if you're really not.
Right. And then the opposite is true if you're going from a high to a low, where the impact pressure on the pitot tube is decreased, and therefore it thinks you've slowed down.
That's exactly right.
So is the risk in that, in terms of a pilot's reaction, one, if you're going from high to low, you might think you need to increase power and then risk damaging the plane by throttling too much power, if you're not paying attention to your RPMs, by the way. And the opposite, if you're going from low to high, you might be tempted to reduce power and potentially stall the plane. Again, assuming you're not looking at your RPMs.
Right. Where they want you to apply the application is from an pressure altitude perspective. They want you to learn it so that you know how to do high elevation takeoffs and landings, particularly landings, right? So when you're coming into like a mountain airport, high elevation, and as you know, as pressure altitude increases, pressure decreases significantly. And then what they'll ask you is, okay, you're flying into a mountain airport, pressure altitude, 8,000 feet. What do does your true airspeed increase? Does your ground speed increase? How do you fly your airplane? And so because pressure decreases, at the very and here we go again. I like to get fundamental about it because that's how I understand things. But at the very most fundamental level, for your airplane to actually perform the same as it does at sea level up in the mountains, you have to have the same amount of air going over the wings, right? The same amount of air molecules going over.
So the indicated airspeed remains the same.
So your true airspeed, meaning the speed at which your aircraft is traveling relative to the air molecules around it, has to go up, has to increase, right? Because there's less air at high altitude because there's less pressure, right? But your indicated airspeed will compensate for that. Your true airspeed goes up, but because the impact pressure on the pitot tube goes down because of the lower pressure, your indicated airspeed is going to be the same at a mountain airport as it is at sea level.
Yep. That's something I remember from one of the earlier conversations with you, is that trick question of, you're always going to have the same indicated airspeed when it comes to, like, for instance, landing your plane, but the other airspeeds may be different.
Exactly, based on wind and pressure and the whole deal. Yep.
I have to remember. I think true airspeed, the relative airspeed. Okay. Every time I learn one more thing that my goal for every lesson is to walk away feeling better about something I felt uncomfortable about going into it. So this is good.
There you go. Yeah, man. No, that's good. These two, I'll be straight up with you, man. These two questions about pressure and altitude speed have haunted me. Like, haunted me. It always comes up on a flight review. When you go to get checked out in a new airplane and an instructor wants to quiz you, these are the ones they bring up, and I'm like, screw it. So.
Yeah, I could see that.
Yeah. All right. Cool, man. Anything else you can think of while we're on the phone?
Yeah, there was one from the quiz. Shit, I locked my other computer, so I don't have the exact number on it. It was one of the first ones. I think it was like the third or fourth one. And it had to do with looking at the figure with the I just forgot the name of it. The one with the circle and the pattern indicators.
Yeah, I'm pulling it up right now. Just a sec.
It showed the wind socket, and it said, which way are you approaching? Is it like a quarterly this or quarterly that? And I just simply don't remember. So question, maybe it's on the second page. No, go back to the first. I think it was question number 4. Yeah, 3809 there at the bottom. So I didn't know what a right quartering headwind.
Segmented circle indicates that a landing on runway 26 will be with a. Okay.
Oh, now I see it. Headwind versus tailwind. I got so hung up on the quartering part that I failed to recognize the question. So runway 26, which would be the left-hand side one, it would be a left-hand turn with a quartering tailwind, right?
This would be 26 right here.
Why is that 26?
Because north is up and west is this way.
Oh, son of a bee. You head into the direction of the runway. Right. Okay. So that would be, it'd be a right turn with a quartering headwind?
Yeah, I think that's it. Yeah.
Right turn with a quartering headwind.
Yeah, right quartering headwind. Yep.
Okay. That's going to get me. I know it. I wanted to put the number on the runway on the side of the compass that it was on, not the direction it was pointing.
That's it. You know what, though? Those are the things that you polish up on with real flying. Like once you jump in the airplane, man, you're just going to, because you're going to have to you'll be staring at the damn heading indicator while you're on, while you're doing your flying, and you'll know exactly which direction you're going with the runway and all that. So
Yeah, I spent some time last night watching and learning videos on patterns, how to fly the patterns. I think I finally have my head wrapped around that, and just sort of like the teardrop entry, the parallel entry on the downwind, the direct entry, the 45 degree on the downwind is where you want to enter, and the base final, short final,
yeah.
crosswind, upwind. So just getting familiar with that, and the 1,000-foot altitude is where you want to enter. And if you're going to fly over the airport 500 feet or above, if they have jet engines or turbo, you want to do 1,000 feet above because they have a higher altitude in their patterns. I'm just trying to, when I get in that plane, I just want to focus on flying it.
No, that's exactly right. I'll be real interested to hear what your instructor's opinion is on pattern entry techniques, because like I said, it used to be acceptable to enter on a crosswind. At least that's how I was taught. Maybe I was taught wrong. But and now it's like it's 45 degree on the downwind, and that's it,
Yeah.
Now at Sugarland, you will get the opportunity to do what they call non-standard pattern work, because it's got a control tower. So they're going to make you do all sorts of crazy shit. Just based on traffic, right? Like if you're coming in for landing and there's like a citation on like a 6-mile final, and you're like, oh, I'm going to enter on a 45 degree downwind, the controller's going to be like, no, I need you to like enter direct on base. And you need to make a short approach, meaning basically when you finish your base turn, you're over the numbers.
Yeah.
So yeah, there'd be a lot of that going on because of that airport's a little busier.
Okay.
So yeah, man, excited.
Cool, man.
I'm actually, I hopefully, it would be a lot of fun for me anyway. When we come down to visit and you have a flight lesson, I can ride in the back seat.
I will totally see if we can get that to happen.
Okay. Yeah, that'd be cool. And then I can tell your instructor that I was a ground instructor, so I deserve at least a ride around the pattern.
Oh yeah, well, I'm hoping to reflect well on you by being prepared, but when I show up a week from now. But one of my goals is to, in December, have my license and be able to fly somewhere to meet up with you and Emily in the hill country for like a brunch or something, and just kind of enjoy that moment. So I think that'd be really neat. My goal is by the end of the year to have it. So I'm gonna.
Oh man, that's awesome.
Yeah, well, I figured if I can get 2 to 3 lessons a week averaged, and if I can learn right around the average pace of the nation, then I might have a chance if weather plays nice. But,
yeah, I agree. I think you've got the weather thing on your side for sure. A lot of students up north have to stop doing their flying in like November. But the one thing you're going to want to do, obviously your instructor will coach you on timing, but since you're pretty comfortable with learning things concurrently with one another, you're going to want to pick up a copy of the flight test protocol. It's called oh shit, it's got an official name. I'll send it to you. But the FAA publishes the exact protocol for the flight test.
Oh, like what my check ride will look like?
Exactly. It's like word for word. So everybody gets a little nervous, obviously, for their flight review. I mean, if you didn't, it'd be strange if you didn't. But you can like basically mentally prepare for exactly how it's going to go. Because they take all the ambiguity out of it. They publish every single thing that the examiner is going to do.
Sweet. That's good news.
So I'll send you a link to that. I mean, obviously it's too early now, but probably when you're like maybe 20, 25 hours in, it doesn't hurt to start looking at that.
Yeah, maybe like right around how far in do you typically go before you solo?
So I mean, I could see you probably soloing after maybe 12 hours, 12, 14, 16 hours, somewhere in that time frame.
Yeah, these guys follow that really strict Cessna pilot school program, so it may be that it doesn't matter if I'm ready. It's just whether or not I'm far enough along in the program.
Oh, okay. Do they have an hour? Do they have an hour requirement?
I actually don't know. I just know that they've talked a lot about how they have a sort of a regimented syllabus and that they like to stick to it. And that's why I have to do this King School thing online where I have to watch these videos and watch these PowerPoint slides. It's been great because it's been reinforcing everything we've talked about. So it's nice to have that constant reinforcement. And like I said, it helps to clear up some areas where maybe I was a little confused and didn't realize I was confused. So the interactive has been so critical, so I can ask questions. I can't ask questions of a video. I can't ask questions of a PowerPoint slide.
Mm-hmm.
I can ask questions of a person. Now, I think their design is that you would do this with your flight instructor as you go along, but
Sure.
that's not the route I'm taking. And I'm kind of glad because it's a lot of information, and I think this will reduce the amount of time I have to spend in the plane to get my license. Like instead of taking 65 hours, which is like the national average, it may take me 55 because I had done so much front-loaded work that I was really comfortable with the concepts and I was able to more quickly apply them because I wasn't spending time in the plane learning them. I was spending time in the plane applying them and getting comfortable with them.
Well, yeah, and I think your commitment to do a couple lessons a week, it's definitely not linear, right? If you can do a couple lessons a week, that will exponentially improve the hours. That'll get you closer to the 50 hour mark.
Yeah.
I did probably once a week, maybe once every other week back in the day. And it's when you can like go to the airport 2 or 3 days after you were just there. I mean, that's definitely valuable.
Okay, cool.
So cool, man. Well,
Well,
do we? I just meant to look at the calendars. Is this a Sunday class weekend, or is
I
this?
don't think so, and I think we're off next Thursday. I will be in the boonies, so I won't
That's
be able
right. Yep.
to log in. If you guys do want to have class, feel free to go ahead. I can watch the video. I know I'm committed to doing that. I think on the calendar we said this Thursday would not be a Thursday class.
Right. Let's see. Today's the 17th, right?
Correct.
I am not showing any class this. Am I? No, I'm not showing anything this Sunday. I'm showing a full week.
Yeah, that's what I'm saying. Like we had class last Sunday. We're off
Okay, got you. Okay.
Thursday because I'll be. I remember saying at the beginning of the course that I was going to be out of touch.
That's right.
So.
Yeah. Well, no, that's good. That's cool. So we will resume then 27th, if I'm not mistaken.
Yep, Sunday at 1:00.
Perfect. Awesome, man. Well, hey,
Cool, man.
send Sarah our best and have a good night. All right, dude.
Likewise, telling me to say hello.
Yep, you bet, man. See ya.
All right, later.
Later.